working. Yeah, that should do it. If you say anything weird about the recordings or missing lectures, anything along those lines, please let me know. I'll try to correct it right away. Well, welcome back, everyone. We're on our second day of our midterm week. I hope midterms aren't too terrible for everyone so far. But any questions while we get started, folks? Okay, well, let me bring back the. Oh, I can't bring back the announcements. I forget. If you reshared, all that annotation's gone, but that's okay. We can do it kind of the old-fashioned way by just pointing at things. We're nearly done with our section 5.4. We're just finishing off our last example there. And once we're done with that section, I think it's a good idea to just pause, catch our breath, and review several chapter 5 problems, ones that would make great candidates for a real exam setting. That's what we'll be doing right here on our chapter 5 review. I'm thinking that might take a couple days to get through. So probably about half of Wednesday and Thursday, we'll be reviewing for all these sections on exam, maybe more of a focus on 3.4 to 4.2, since we'll essentially start reviewing for chapter 5 once we're on that document there. So that's our goal so far for the week. Any other questions, folks, about the upcoming exam or anything interesting on WebAssign or any of these problems folks would like to discuss? Okay, well, let's jump back to right where we left off on our section 5.4. And 5.4, I think I have a clock right here, so it's kind of embarrassing. I think I just lost track of time. It's kind of a fun problem in a way. And we had to stop right here. We were building up the table and we didn't get this fully constructed. I put that question mark, the giant question mark you see right here, just as a reminder that that's what we need to return to finish building up this table. So let's briefly just remind ourselves about the context. We're looking at penalty goal kicks. The events in green are what happens with the goalkeeper, who will either move to the left, stay in the center, or move to the right to block the kick. The event B is really relative to the penalty kicker. Either his kick will be blocked, or we put B complement as well to say, well, that's the good thing. The person would have scored a penalty point. So in building all this, really it was kind of tricky because with our brand new table, we could do these probabilities in the normal way. We just took probability of L, multiply it by 1,000, got 493, and just dropped it down there. And kind of just rinse and repeat. This multiplied by 1,000 is 63, so we put it down into that total. 444, threw it down into that column. But then after that, we're pretty much stuck. We need a new way of getting the counts right here. Particularly the counts in red were the major idea. And although we've done this once already, let's try this a second time, just to get a feel for how it should go. In orange, I'm going to delete this in a moment. Think of this as really just scratch work. If you want to calculate, say, that probability, where it's 0.333, it's conditional, so probability of B given C tells us all we care about is being in the column for C. So we could eliminate all the information here, all the information here, and here temporarily. Then we would take 63 for the denominator. B would be blocked. There's 21 potential outcomes, so 21 would go up into here. Then we would just take 21 divide by 63. And that's where the probability of 0.3 repeating, it looks like, was coming from. Just taking the 21 divided by 63, essentially. But then we mentioned, well, how... Oh, I deleted a little bit too much on that one. The way we actually got these counts right here, the 21 in particular, was we did this in orange right here in reverse. We essentially just took the 63, multiplied it to the left-hand side. So there's our 63 times probability of B given C, and we got the count of 21. So that's the idea of doing this kind of thing. It's just like calculating a conditional probability, but we're unwinding it. And so all the steps now going backwards. Well, does that make sense, folks, at the moment, before we try a new one? Okay, let's give this one more try. So we're now thinking of this probability right here. Probability of B given R blocked, given that the goalie went to the right-hand side of the goal. We'll take our, to get the pen working, count to 444. We'll multiply probability of B given R and get this result. 444 is now multiplying the value of 0.126. We'll round this to the nearest integer and let's see what we get on this one. So 444 times 0.126 gives us this as a count. We don't want to put in 55.944. Here's where this comes into play. Round to the nearest integer is meaning we'll round up to a 56 on this one. So right here, we'll put in 56. Then the standard thing, take your 444, that entry down below, subtract off that 56 we just found, and we have that last count, 388. So 388 will go into this location right here. I'd say this is kind of the nastiest table we've gotten through so far, but conditional probabilities just give us this weird new way of getting values in. And I think that's the whole confusion. If you're comfortable seeing how we calculated the conditional probabilities, say, particularly these ones where we really focused on just one row or column, then this is really the major idea of how we got through that problem there. Well, we're almost done with the table. We should do our row totals. So let's let that be our final step. So it's going to be 70 plus 21 plus 56. We get a count of 147. And last one, 423 plus 42 plus 388. Now there's two ways to do this one, right? You could have just taken 1,000 minus 147 and that would work. Or total these together and we get the value of 815. Let me take another look at that 423. Oh, that would be a mistake right there. I was getting nervous with 815 because there's no way I can put 815 here and get 1,000 even, but I put 4 instead of 42. So let's correct that. So we have now 853. That looks a little bit better for actually summing to 1,000. And yeah, looking at it, that would exactly come out to 1,000. So we've got it, folks. That's our hypothetical 1,000 table finally. Any questions or comments at all constructing that kind of a monstrosity right here? Yeah.
When you're actually putting in like the given values in the chart, will there ever be like a circumstance where the value won't just go like in the intersection spot, or will that like always happen?
I think for this, it would definitely always happen. Yes. We're only ever going to get one particular count. So no matter where we put these values, they're always going to be in the intersection of something in just one location. Say, for example, the count 56 is the intersection of B and R at the same time, blocked and the goalie went right. Does that make sense about your question there?
Yeah.
Gotcha. So in other words, anytime we do this kind of work, you'll never be in this sort of problem. Let's put it up there. Maybe that's a better spot. The problem I'm looking for is oh, it's not on these notes. That would explain it. There's a problem where we're dealing with a union and we have to spread out the counts over 3 different cells, but that would never happen in this kind of problem. We do have one of those in our review section, however, that we'll definitely make sure to take a look at. But other questions so far? Okay, well, let's give this next follow-up questions a try. Now that we have the table, everything is just based off this information here. I'll take a quick screenshot as usual, just so we're not scrolling up and down to see the table. And finally, here's our follow-up questions. Once I kind of, oh, that's not a good idea. Let's fix that. There we go. You can kind of flip things around if you zoom them a little bit too aggressively. And I'm not sure what that was either. Computer's really pissed off. I think I know what that is. I think that's sticky keys. Is it on? Okay, I think it's back to normal. If you press a button on the keyboard or hold it or something like that, you get the accessibility tools come up. I think that's if you're kind of blind. It's trying to tell you what you're doing. Not too sure on that, but I think we're ready to start, folks. On part B, it says, calculate the probability of B complement, give a practical interpretation using the context, and we'll round that to 4 decimal places. So this one is a little bit weird. Usually we have, say, an intersection or a union or even a conditional probability to work at. This is only, I think, the second time in these notes that we've had to deal with something like that. But the way it goes is actually pretty fast. Go probability, B complement. That means we're really concerned about this information right here. In particular, the total is what we want, 853. There's 853 ways in the hypothetical 1000 table that B complement occurred, meaning the kick was not blocked. That was a successful goal kick. So this will be 853 for the numerator. Divide by 1000. And we get 0.853 to solve that problem there. Well, these are kind of fun. It's really just one count we had to take, the 853, and divide by the typical 1000. And the practical interpretation is not too bad either. For this one, we can say pretty rapidly. Let's just mention the probability to start it off. There is a 85.3% chance that, so after we say the probability, go inside the probability statement, and we're just trying to read out what does B complement actually stand for. Well, you can always, if you're not sure, go up to where B is defined. B is the event that the penalty kick is blocked. That means, well, B complement, we'll just say is not blocked. So there's an 85.3% chance that the penalty kick, and you can always say was not blocked. That's completely accurate. But if you feel like just some more ordinary words might be okay, that should be just fine. So instead of saying the penalty kick was blocked, let's just say the penalty kick was successful. Meaning they did score a point on that kick. So if you want to, you can change the wording here a little bit. You don't necessarily have to read this out verbatim. Well, any questions, folks, on this one here? Okay, we're off to a great start. That's our first probability computation. And really, after constructing the table, every computation goes really quickly here. So let's try this once again. Make that a little bit bigger. This one, we're dealing with a conditional probability, so we need to be very careful in how we calculate it and how we interpret it. So it starts off by saying we want the probability of C. This means the goalie stayed in the center, given event B. Now, there's always a great way to think about these. If it says given B, then our entire table cannot be reduced to essentially just this. So from here to here, we just saved the row, and the row that had the L, C, and R given as well. We need that C right there, since we're asking essentially, what is the probability of C if all you care about was the kick was in fact blocked? It turns into a fraction, just like on the prior problem. Anyone spot what the denominator must be in this situation? Exactly. Yeah, we will have 21 for the numerator. That would be relative to the event C. So 21 goes here. And absolutely for denominator, 147. So that's pretty much it. We still want to round this and get a value rounded to 4 decimal places. So this will turn into 21 divided by 147. We now have a probability of 0.1429. All that's left to do then is give that practical interpretation. So for that, let me redo this here. So these ones, again, they're a little bit tricky because our interpretation has to capture the fact it was a conditional probability. In other words, we have to give an interpretation that matches up with the fact our table is just this. That's all we use to calculate the probability. So another way to do it is you could say among all the penalty kicks that were blocked, because that's all we're looking at. Or that's the condition, the given information here in the conditional probability. Let's say here, among all blocked penalty kicks, okay, so that's my first bit in blue. All I've done is matched up that conditional there. Any volunteers for what the rest of the statement should read out as? Yeah, go ahead.
There's a 14.29% chance for that to be something.
Exactly. So we'll convert that to percent. There is a 14.29% chance that, and then you said next, the goalkeeper stayed in the center. Awesome. The goalkeeper stayed in the center. So we did it, folks. That's our interpretation of that conditional probability right there. Just trying to fix the penmanship. And the way we analyze this, again, there's always a couple options, but the way we analyzed it was we first mentioned the event B because that's what we restricted all of our attention to. The whole sample space became that event. Then second, we converted that to a percentage and just said 14. Oh, and I forgot my symbol. You know, actually, that's okay because I did say percent chance. That would be redundant to put a percent symbol there at that point. Then the third thing, we just said what the event C was, staying in the center. So again, I think this is a good interpretation. It's not the only one we have to give. It's trickier because we bounce all around to give it. I feel like this is the interpretation just about everyone would understand, even if they haven't taken a statistics class. And that's always kind of the gold standard. Try to write an interpretation like that. For the sake of an exam though, if you want to just write it out in just kind of a formulaic way, it could look like this once I get the cursor to work. So an alternative solution, this always would give full credit on exam. And it's in the spirit of what we're trying to do. If you have a probability statement, you can always just break it down by going right, going inside here, reading left to right. So that solution would look like this. There is a 14.29% chance that, we'll say here, the goalkeeper stayed in the center. The vertical bar will just literally say, given that. And given what? The event B, that the kick was blocked. So that's just fine as an interpretation as well. To me, I think it's confusing because it's not necessarily clear what we're saying when we say given in this kind of context. What we're really saying when we say given is just among all the blocked kicks and nothing else is the real meaning there. Well, we've solved it and we gave 2 interpretations. Any last questions, folks, on the notes here? Yeah, go ahead.
So when we're solving for the given second letter like C given B, like what we're narrowing, our options down to is like always in line with that letter, right?
Exactly. Always the second option is where you narrow things down to. In fact, that's such an important comment. Let's put it here on the notes just to really make that last statement here. So I want to go from here to here with an arrow and just explain this by saying the given information, or let me try one more time with the arrow. We should point that way, the thing that survived. The given information after the, I want to say bar, that vertical bar here is what I'm referring to. So the given information after the vertical bar is the only information to survive. In other words, we essentially disregard or blacked out or deleted everything else in the table other than the labels LC and R. All the other counts are just wiped out. So anything that comes second is the thing that is always going to be left standing. Other questions about that so far? Okay, any other questions at the moment before we go to our chapter 5 review? Okay, let's save these down. Thinking about it. There it goes. And now we are done with probability, essentially. We still have to review, we'll still have to get through a second exam, and we'll still be doing probability here and there. But let me go back to the start of the class, since it's always good to remind ourselves, why in the world did we do chapter 5? Because it's definitely a slog. It feels even out of place for a class like this one. But this is the whole reason. Back to this situation once again. We'll be pointing at this a lot until we get to confidence intervals and hypothesis tests. But this is where we're at in the process so far, once I get these tools to work. Okay, so the reminder on this problem was we just had a population and a sample. We drew a simple random sample of size 100 and calculated a statistic. That statistic, the sample mean X bar, the average GPA of those students, was approximating something that's completely unknown to us, the population characteristic mu, or the parameter value. Because it's unknown, we have an extra problem right here. Sure, it's approximately equal to the sample mean X bar, but we need to describe the accuracy. And here's how chapter 5 is finally going to help us with that. In describing the accuracy, we will find numbers A, B, such that the probability that something unknown is between A and B comes out to whichever accuracy we want. We could be highly confident or highly accurate or in the middle of the road, but a typical value for here, not special in any way, but just a typical default generic choice would be 0.95. So we have a probability statement, and the thing that's going to go in the middle is the thing that we cared about really at the entire start of this study. You would have only considered this population and run this whole study if you're trying to come up with what is mu. It's close to the sample mean, but we'll find numbers so that the sample mean is between A and B exactly, and we'll be able to say the probability that the mean population of all students at ISU is between those values with a certain percent chance. So that's our huge takeaway of why we went through all of this in chapter 5, to understand these probability statements and get used to giving interpretations for them. Then we'll later say that this thing, AB, the interval A to B, and math, we're just referring to a set of numbers starting at A, ending at B, not including those endpoints. Just writing them out as AB is called a confidence interval. So after we can finish our chapter 5, which we're just about done with, we'll be doing some more work with the normal distribution. Strange as it seems, the normal distribution does fit into this picture. So let's see how to calculate it, not with the empirical rule, but even more accurately through a calculator. And we'll be doing confidence intervals right after that, very, very shortly. So again, we're over the hump. Chapter 5 is the difficult material. And the major takeaway is understanding how to form and interpret these probability statements here. Well, any last questions, folks, before we take a look at the review next? Okay, I'll take a screenshot of this just so that if you're curious about the statements here, there'll be a place to come back to them. And now we're right over here on the Moodle website. The chapter 5 review problems. Now, if you printed this out early, I have to apologize. I did make some edits, and I think I finally decided what the document should look like probably around 12:30. So if you printed it before 12:30, there's been a few changes and edits around on this document. And here's what it looks like. It starts off with some pretty generic kind of examples. Example 1, example 2, they look kind of boring and simplistic. There's no context. My goal with these two examples is just to show what some major formulas are. Then the problems that would make actual really good exam problems will start on example 3 and example 4. These are pretty long, so they're good questions for an exam, but I wouldn't ask this many parts necessarily. So that's what the notes look like, and let's give this a start. Again, example 1, example 2, a little bit strange. They're not great exam problems, but their whole goal is to remind us of formulas that are on the table that could be useful. Starts off by saying, assume that Q and R are independent events. P of Q, the probability of the event Q is 0.4. Probability of the event Q and R is 0.1. Our whole goal is to find the probability of R, P of R. But really the one big thing that they told us that we really ought to put down a formula and start using right away is this statement here. Q and R are independent events. The confusion here is this gives us two formulas, and the formula we use is depending on the situation. So one formula based off having independent events goes like this. Probability of Q intersect R is equal to the probability of Q times the probability of R. So that's one formula we get completely for free just from them telling us we have independent events. And here's the second one. Independent events means the probability of the event Q or the event R has nothing to do with the other event. So we can write out probability of Q given R must be the probability of Q. Because whether R was given or not will never influence that probability if those events are truly independent. So those are the two formulas we get to use. And let's take another look. We know probability of Q is given. We have probability of Q intersect R. So probably we're going to be using this formula right here. But let's add a little bit more information. If you're just told your events are independent, you're probably using this. If the question is, are they independent events? Show this. You are probably using this instead. I think we last time called this one test for independence. There will be a problem on this set of notes where we have to use that test. So I'll come back here and take a screenshot exactly when that comes up. So if they say, are the events Q and R independent? If that's the question, we need the test. But if they just tell us the events are independent and we have something we have to work out involving intersection, we'll just use this formula instead. So that's the idea so far. Any questions at the moment? Okay, so our goal is to find the probability of R let's start with the intersection right here. We're told that the probability of Q given R is 0.1. We also have the probability of Q as 0.4, so we need that information there. Let's begin by writing probability Q intersect R by independence becomes probability of Q times the probability of R. So that's my first step. And at this stage, we've used up independence. I can't do anything further with that information there. But coming down below here, we can make some substitutions. On the left-hand side, probability of Q intersect R, that's a value of 0.1. So we can just drop that in right over here. So here goes 0.1. That's one substitution down. A probability of R here, we can't do anything with that. That's the question, to find its probability. But we do know the probability of Q. That one was given as 0.4 right here. So 0.4. Then it multiplies the probability of R. And that's our work so far. Any questions at the moment? Okay. I forgot to put in that screenshot, so let me put that in right here. The screenshot did survive, and we're back to right here. Okay, so at this stage, the whole question was to find the probability of R. We're essentially there. We could just divide by 0.4. Probability of R is now 0.1 divided by 0.4 equals probability of R. So this is essentially 1/4, and we get 0.25 is the probability that the event R occurs. So that's kind of the punchline with this right here. Usually when we're told events Q and R are independent, just told it, not asked about it, we would use this equation right here and then break it down with the hypothetical 1000 table, like we did in section 5.3. Well, this problem, we're just trying to find the value probability of R. Any last questions, folks, on getting through this example? Okay, so the big takeaway on this particular example one is, once again, the two different formulas that you will get anytime you're told events are independent. Let's try this out again. For example 2. The two specialty kind of events were events that are independent, but also events that are mutually exclusive. We're told right away on this problem, assume the events U and V are mutually exclusive. Again, a weird problem. There's no context here. It's really a math problem more than anything. But our purpose on example 2 is just to put down some information and some formulas. That's a huge assumption, just like independence is. Let's first write down what that means just in words. If we are assuming U and V are mutually exclusive events, this means U, V cannot occur at the same time. If you're talking about things happening at the same time, there's an and statement buried in there, which is conflated with the intersection symbol. So just these words alone are what's giving us the formula. Probability of U intersect V, and I wrote that U in kind of a weird way. Let me try again. It's good to try to make your U look like the letter U in some way, any way you can. Anytime you're doing a union or intersection, try to make them look like this. That's the intersection. The union would look like that, just inverted, not like the letter U. Kind of a weird choice to have U next to one of those symbols, but something to get used to. Probability of U intersect V will take a specific value right here. Anyone recall what it must be? Exactly. And we can kind of reason through it right here. If they can't occur at the same time because they're mutually exclusive, you will always get probability of 0 right here. So that's our one equation we get from mutually exclusive events that can't happen at the same time. Well, so automatically, You could form a statement involving intersection that has a probability of value of 0 every single time. Well, that means we answered part A, right? Probability of U intersect V is just 0. Let's write it down again, just so we have it down. Probability of U intersect V is 0. The formula is right here, and we've done it again. Well, I did say something that was maybe not fully accurate. I said the one formula you get for mutually exclusive events is this. Actually, there's one more. We just haven't used it a lot. Honestly, we probably wouldn't use it over here. We'd really use a hypothetical 1000 table. Let's just mention it just because it is there. We shouldn't ignore it. If your events are mutually exclusive, this is the one time you get to use a pretty interesting formula. Probability of U union V would be equal to the probability of U plus the probability of V if there's no way U and V can occur together. You can just add up the individual probabilities. Do folks recall doing that before? It's been kind of a long time, honestly. The one time we really kind of used this formula was all the way over in section 5.1. We had mutually exclusive events because we reasoned there's no way the hardback could also be a paperback, so we assumed that there's no overlap there. And we were just assuming that a digital book does not overlap with the audio book, with the way the bookstore is classifying all of their books. So when we were asking for the probability of digital or an audio book, we called it probability of D union A, and we just took the probabilities and add them together. This only worked because there was no way for a digital book to also be considered audio, at least in our consideration for the problem. Back over here, we could do it the same way and say probability of U union V will just become the probability of U plus the probability of V. And we can now look up those probabilities. Probability of U is at 0.26. Probability of V is at value 0.37. So we get all together, oh, let's see, that's addition with carry, looks like a 0.63 altogether for this one. So those are two formulas. I would say this one right here, that's kind of indicated as more important with the better colors. This is the better formula for just the purpose of preparing for exam 2. I would say that's the bigger takeaway. Well, we did it, folks. That's our second rundown. Again, the whole purpose of example 2 is really just to consider this formula here. Any questions, folks, before we turn to the next longer example? Okay, so the takeaway is there are two formulas for independence, and they're situationally specific. Sometimes we need to use this one right here. We'll see that in the notes. But when it comes from mutually exclusive events, the exam is really going to be focusing on this formula here, not so much this one. Really a consequence of using the hypothetical 1000 tables. We just didn't have cause to use that formula as often. So here, these are now the questions that would be considered pretty decent exam questions. Aside from, I wouldn't give you like 5 different parts. It's probably going to be maybe the hypothetical table and 2 to 3 additional parts, maybe more like 2, I'd say, for these kinds of questions. Well, let's give this a try. It says 45% of Americans like to cook, 59% of Americans like to shop, while 93% enjoy at least one of these activities. It's a totally made up problem, but still it's a good one for practicing a hypothetical table. First thing we need to do is start saying what are the events we really want, trying to organize and label first. So we're told 45% of Americans like to cook. That will be our first event. We could call this, say, an event C, and then down below, probability of that event C is 0.45. So that's one down. Next, it says 59% of Americans like to shop. That's our second event, liking to shop. You could call this event S. It's a little bit of a confusing letter for that because S could mean a sample space, but you could get away, if you would like, by calling it SH for shopping. So now it's definitely not a sample space in that case. If you called it just an ordinary S, that would be okay because it's in the context as being a particular event this time. Now notice the thing that's nasty about this problem. Probability of shopping is not 59 unless you throw on that percent symbol. But if you put on the percent symbol, that's honestly kind of confusing if you're doing a hypothetical 1000 table, because you don't want to take 1000 times 59. You want to take 1000 times 0.59. So this is a really good situation where the decimal numbers are just better, especially for this part right here. So we have one last one that says, while 93% enjoy at least one of these activities. Let's put that in the purple color since that's the tricky event. It'll look like this. Probability of something equals 0.93. When it said at least one of these activities, we're still talking about C for cooking, liking to cook, and SH for liking to shop. Any volunteers on what should go in the middle? Are you indicating going this way? Yeah, that should be the union, absolutely. So this will be union. Now let's put it here on the notes how we knew that. What was the buzzword? It was really when it said at least one. At least one is saying C or SH, and the or there becomes a union symbol. So that's how we decided union right in this location. Does that make sense to folks about that buzzword right here?
Does that also mean all
It's absolutely, it would be one or the other. And let's put this here, just to be careful, because that would be part of the interpretation, or both. Other questions at the moment? Okay, now that we have our three probabilities, it's not too bad. There's an extra step with this right here, but if you practice this a few times, it's not terrible to get through. We'll start by just writing down the structure of this table. And just a reminder about the hypothetical 1000 tables. There was one table at the end of the notes we just finished, 5.4, where we had to deal with conditional probabilities. I won't be asking that one. There'll be more of these kinds of tables we are doing in section 5.3, where we were building them from scratch. So now it doesn't matter what events you put here, but they should be paired with their complement is the only requirement. I'll put C, liking to cook, in this location, and its complement in this location. C complement always looks funny. It's C to the power of C is what it looks like. But by the red dot, this is just saying the person does not like to cook. So total goes here. Throw in a vertical bar. And now the other events. SH for liking to shop. SH complement for not liking to shop. And total. 1000 finally goes here. And now we're ready to throw down probabilities we're expecting for these two values here, the simple events. Simple meaning just one actual outcome or event is inside here. So for this one at 0.45, anyone see what number you ought to throw right here? Exactly. We'll just take this number here, multiply it out by 1000. So 450 goes right in this location. Now, if you were doing it as an exam, I think this is what a lot of people would probably do. Just throw that number right there. But for a paper trail, for the sake of the notes, never a terrible idea to just put it down somewhere. 1000 times probability of C is 1000 times 0.45, which is what got us the 450. Then we'll do it again, 1000 times. Probability of SH will be 590. Because it says SH right here, we go to that column and drop in the value into this location. 590 ought to go there. And now this one is the tricky one. We're going to spread that out amongst all of these different cells right here. But first, before we do that, I want to show it in two different ways. The way you might do it if you're, say, an exam setting, just throwing things into a calculator, getting a number out. And then I'll show the careful step-by-step way of producing it. So the notes of how to come up with those numbers. So if this was a real exam and all I saw was this table, here's what I would do to start. I would take 450. So the row total here for event C, add to it the 590, the column total for event SH. When you add those numbers up and get the value of 1040, the thing in the middle, which is the intersection, is now double counted. So we can extract the double counted value by now taking this thing, multiply it by 1,000, and now it's 930, but that 930 does not double count at all. So subtract 930. We get a value of 110. That's a value that was double counted in the middle when we took the total 590 and the total 450. So 110 must go exactly there.
Step I always have to solve it.
Oh yeah, absolutely. So right here on this one, I would take 1,000 times
Oh,
the 0.93, giving us that 930, subtracting away from the 1040 here. So that's how it goes into right in this location. But like we mentioned, if you could get a 110 right here, you don't have to show the steps on your exam. No work is required for this. But let's put it down here, again, just as a paper trail. You're welcome to have notes on exams. I feel like those would be notes I would put on this exam. If I was stressed out on an exam, I could forget this and just be unsure of how to make it happen. So here's the procedure. Step one, take the 450 plus the 590. I believe we got 1,040 out of that. Let's double check the calculator here. Yeah, we have 1,040 for that value. Step two, take 1,000 times this event right here. I'll indicate it as 1,000 times probability C union SH. That comes out as 930. Then last thing we have to do in step three is take the larger count, 1040, minus the smaller count of 930. This came out to 110. And so finally, that's the value that goes right here. It always goes directly in that location here for the intersection. And once you have that, the rest of the table is now solvable in a pretty orderly way. But again, this is the big takeaway right here. In an exam setting, just take 450 plus 590 minus 1,040, or excuse me, minus the 930 by that red dot, and that'll work out. Or as a sequence of events or steps, that's how we really got that value as well. Here's the last thing we'll do. From the 590, take away 110. That would be 480 on that operation. Now over here, take 110 away from the 450. We're now at 340 in that location. Let's see. Down here, we could take 450 minus, let me try again, 1,000 minus 450 to get the positive value of 550. Now to the left, take 550 minus 480. That should be 70, I believe. And last computation. From this 1,000, subtract 590, and we should have 410 altogether. Now, if this is a real exam, I would do this as well. Add 110, 340. Doing it in the calculator specifically because I did this as mental arithmetic and I'm not great at that. I want to make sure I get 450. Take 480 plus 70. That one should be easier, 550. Then 590 plus 410 gives us the 1,000 we're expecting. If you could add across rows and get your right totals, you do have the right table. If you could add across columns, get the right totals down below, you have the right table as well. But we did, folks. That's the hardest step of example 3, coming up with that table. When we come back, we'll answer the follow-up questions and then take a look up at the example 4 down below. Well, any last questions or comments before we call tonight? Okay, well, have a great night, everyone. Hopefully the weather is not crazier out there. Stay dry, drive safe. If you do have questions, I don't have a class out on Tuesdays, so I'm happy to spend extra time addressing those questions.